Welcome everybody to our this angular projection discussion. Right here, we are going to discuss this topic when something is projected with some velocity u, making some angle theta with the ground, then how its path is going to be and how it behaves. So right here, we have drawn an example that the object has been projected with some angle theta with the ground, and this is the trajectory that it follows, and this trajectory is what we call as the parabolic path. So it is parabolic path the object follows, and this object travels this much distance horizontally, which is suppose x, and the vertical height with which uh, the vertical height to which it rises up to is h. This is the maximum height h up to which the object rises up. So when the object has been projected with a velocity of u with some angle theta, so obviously it does have two components. One component is acting along the horizontal direction, which we call as UH, and the other component is acting along the vertical direction, which we call as UV. UH stands for horizontal velocity, UV stands for vertical velocity. UH is U cos theta and uv is u sine theta. So we must know how to resolve the vectors. So if we can understand this, the component of u acting along the horizontal and vertical direction, then this is u cos theta, u sine theta, very clearly understood. Otherwise, for the vector resolution, I will have another video for it, how to resolve the vector into the components. So UH is what we see is acting along the horizontal direction, UV is acting along the vertical direction, and you know that gravitational acceleration acts always vertically downward. So when the object is rising up from point A to P, say for an example, the maximum height I labeled it as P. So while the object is rising up to point P, the object is basically decelerating because it rises up against the gravity, so it is decelerating. As it decelerates, its velocity decreases. So right here, to be very specific, which velocity decreases? Horizontal one or the vertical one? It is the vertical velocity that decreases because the vertical velocity is responsible for the vertical motion. The object is rising up, so it does have a vertical motion. Vertical velocity should be considered, should be taken into our consideration. So vertical velocity keeps decreasing when it is rising up. What happens to the horizontal velocity? Horizontal velocity here stays same, constant, because we consider there is no air resistance present. So in this projectile chapter, in this whole kinematics, we do consider there is no air resistance. So the horizontal velocity stays the same all through, but the vertical velocity keeps changing. This vertical velocity decreases while rising up and increases while falling down. So right here, if I want to say that somewhere the object is right there and it has the horizontal velocity uv, which is right here, and the vertical velocity uh, which is always same as before. So the moment the object has been projected from point A, whatever the horizontal velocity it had, it is still the same right here. But uv decreases from this initial value when it was projected. Why UV decreases? Because while rising up, the object had to decelerate. The object had to move against the gravity, so its speed decreases. And this is somewhere where the object rises to its maximum, and here the vertical velocity is absolutely zero. But horizontal velocity is still the same as before. So this is what we have seen from point A to P when the object is rising up. It was decelerating, the vertical velocity was decreasing, while the horizontal velocity stays the same. So you see the u is the resultant velocity of UH and UV. So see, the object has been projected from point A. So this is the parabolic path it follows. I drew U along the tangential direction, and this U has two components. One is along the horizontal UH, other is along the vertical UV. So you understand that the resultant of UH and UV is U. So if you draw the right angle triangle, you will see that it is a right angle triangle. So when you apply Pythagoras, this is going to be the resultant U. So this resultant U also keeps decreasing because of the decrease in vertical velocity. And right here, the total horizontal velocity stays the same. Vertical velocity is 0 at the maximum height. So the resultant velocity u right here is just uh, where at the maximum height at this point P. The resultant velocity is just uh. But before reaching to the maximum height, the resultant velocity was the resultant Pythagoras theorem. According to the Pythagoras theorem, the resultant velocity was the hypotenuse of UH and UV. Since UV was decreasing, so the value of U decreases too. So U had the maximum value at this point A. U keeps decreasing because of the decrease in UV. UH stays the same, constant. So I'm just repeating this thing so that you can understand it. If not, just play back so that you can get it individually. What happens to UH, what happens to UV, and ultimately what happens to U. Now, this is the thing that we discussed for rising up the object. While falling down from the maximum height, the thing just remains the same but little different on UV. That UV now keeps increasing in the downward direction. Earlier, while it was rising up, UV was decreasing. It was decelerating. So UV, the vertical velocity, was decreasing. And now from the maximum height, it is accelerating. So UH stays the same as before. UV now increases. And UV here is again increased more than before, but UH is still the same. And when it is going to hit the ground, the same UH, there is no change in UH throughout its path, but UV here is maximum, and it is as much as right here when it was projected from the point A. So the vertical velocity at point A is same as the vertical velocity at B. Why is it so? Because A and B are on same vertical level. So the object rises up, travels this much height vertically, while falling down, it covers the same vertical height. So whatever the velocity it had at point A vertically, this vertical velocity keeps decreasing and reaches to 0 at the maximum height. When it was falling down, that vertical velocity now keeps increasing at the same rate, the way it was decreasing. Now, at the same rate, it is increasing from 0, reaches to the maximum as much as it had at point A. But direction is different. You see, UV right here is in the upward direction, and while landing on the point B, it is in the downward direction. Just direction is different. Magnitude is same as before. Now, as we already have discussed that the vertical motion and horizontal motion, they are independent to each other. One has no effect on another. So we have to consider them individually, separately. The vertical one does not have any horizontal effect. So if I say this is G, it does not have any horizontal effect along this direction. And the horizontal one does not have any effect along the vertical direction. No effect. So horizontal and vertical, they are completely independent to each other. Now, when we are going to consider the horizontal and vertical motion separately, then we are going to write down the equations like this. So right now we are considering the vertical motion, and when we do consider the vertical motion, how many parameters we can have that are acting vertically? One is the vertical velocity. So we just can consider the vertical velocity here, which is uv, which is u sine theta. U is the resultant, so the sine component of the resultant, because theta is given right here to the ground. That's why it is sine theta. So the vertical velocity we can consider. We can consider the acceleration due to gravity, which is vertically acting. So acceleration due to gravity is g, which is 9.81 for this planet Earth. If it is somewhere else, we have to take that g. Then we can consider the vertical height, which is big H. This is, we refer to the maximum height reached by the projectile, and additionally, since A and B are on same vertical level, that means the point from where it is projected and the point where it is landed, there is no vertical displacement of this projectile. It reached back to the same ground from where it was projected. It did travel some horizontal distance, it did have some horizontal displacement, but there is no vertical displacement. So right here, the vertical displacement is 0. Why it is so? Because A and B are considered to be on the same vertical level. This is why you can consider the vertical displacement to be 0. So these are the parameters that are acting completely in the vertical direction. We have to consider them only when we are considering the vertical motion. In the horizontal motion, we cannot consider any of these things right here we have mentioned. But there is one more thing which is common for horizontal and vertical, which is time. Right here, when the object has been projected, it is going up, then falling down, so it is having the vertical motion. And you see, while it is rising up and falling down, it also covered some horizontal distance. Why is it so? Because the velocity with which it has been projected, it had some horizontal component. So this horizontal velocity is responsible for the object to have a horizontal motion. So right here, we are considering this angular projection to be so important because the object simultaneously has two-dimensional motion. It has vertical motion and horizontal motion parallelly. So this is why the time here is only the parameter which is common for both the horizontal and vertical motion. When the object is covering some vertical motion, it covers some horizontal motion as well. When it has some horizontal motion, it covers some vertical motion as well. So that's why this time is common for both the horizontal and vertical motion. For an example, the object projected from point A and landed at point B, if I considered that how much time the object took. So this time t the object took, and the object by this time t traveled horizontally x meter distance horizontally in this time t. And what did the object travel vertically? Absolutely, it did travel some motion along the vertical direction as well. It reached to a maximum height and then it falls back. So object had the vertical motion as well in this time. So that's why the time is the parameter, is the quantity that is going to be used both in horizontal motion and vertical motion. No other quantities are used as such, just only time. So here we are saying time of flight. Time of flight means how long the object was in the air. So say this is t. Being projected from point A, landed at point B, the time t is the time the object was in the air. So these are the quantities, these are the parameters that only we can consider when we consider the vertical motion. So think, just see what things are left right here. What didn't we take here? We didn't take the horizontal displacement. We didn't take the horizontal velocity because they are completely acting in the horizontal direction and they do not have any influence along the vertical. So horizontal and vertical, they are completely independent to each other. This is what we have to understand, we have to remember. Now we are just going to use same equations of motion, but wisely in a different way. We are right now considering for the vertical motion only the vertical velocity, not horizontal velocity, not even the resultant velocity. We are going to consider only the vertical velocity. First of all, get acquainted with the equations of motion once again. We know V equals to U plus AT. We know S equals to UT plus half AT squared in terms of the initial velocity. This can also be written as Vt minus half AT squared in terms of the final velocity. Then we know V squared equals to U squared plus twice AS. So these are the equations that we already know. Now we are going to make use of these equations right here in this angular projection topic very wisely so that we can get a clear conception of it. So the vertical velocity must be considered, which is uv, u sine theta. So if I consider this equation, v equals to u plus at, then v equals to u plus at is my first equation that I am going to consider. Now, how am I going to consider this equation? Instead of v, I will write vv, the vertical final velocity. Instead of u, I will write uv, the initial vertical velocity. Instead of a, I will write g, and t here is the time of flight. This t is the time of flight, means how long the object was in air between point A to B. So see, whatever the magnitude of uv, the same magnitude is vv. Right here, we didn't change in the diagram, we put uv all through, but you have to understand because the final velocity is to be considered when the object is right here landed because t is taken as the time of flight. So that's why we are going to say uv as to be the final velocity, which is vv. So what is the difference between uv and vv? The vertical velocity at point A and the vertical velocity at point B. There is no change as far as magnitude is concerned, but direction is changed. uv, the initial velocity at point A was acting upward, while the final velocity at point B is acting downward. So magnitude is same, direction is opposite. This is one thing. Second thing is you are measuring or you are finding the time of flight. So when you started calculating this time of flight, that means from point A, you see the object to be moving in the upward direction. As it moves initially in the upward direction, although it comes back, although it falls down, but you have to consider g to be negative for the entire journey, for the throughout the motion of this parabolic path, throughout this trajectory. So right here, if I just write down the Vv to be as a final velocity vertically at B. uv, the initial velocity vertically at A. And you see, as long as A and B are on the same vertical level, So UV and VV, they are going to have the same magnitude but opposite direction. So UV and VV, they are going to be same in magnitude but opposite in direction. So you can put a minus sign here. So if you consider one to be positive, the other has to be negative. And the time started for this time of flight means point A, we see the object to be moving upward. So G is going to be negative all through its path. Although it is falling down due to the gravity, but we have to consider the time when it started its motion. It started its motion in the upward direction against the gravity, so we have to take this G value to be negative throughout its journey. So right now, if I just subject this time, it is going to be VV minus UV divided by G. So say VV and UV, they are going to have the same magnitude but opposite direction. If we do not consider the direction, then this difference between VV and UV are going to be zero, and you are going to get the time value to be zero, which is not possible. So since I considered UV and VV to be in the opposite direction, which is actually the case, and I wrote UV equals to minus VV, so VV minus VV divided by G is going to be twice VV, G. This is the time of flight. And what is UV or VV? It is nothing but U sine theta. The value, the magnitude is nothing but U sine theta. U is the resultant velocity with which it was projected. Actually, theta is the angle it makes with the vertical, with the horizontal in this case. So right here we can say this is twice U sine theta divided by G. This is the time of flight. That is what we got. So this is the first equation, how we dealt with. The second equation, S equals to ut plus half at squared, or S equals to vt minus half at squared. One is in terms of the initial vertical velocity, other is in terms of final vertical velocity. You see, these are the equations only to be considered in the vertical motion because we have acceleration right there, and acceleration does act only in the vertical direction, acceleration or deceleration, whatever you say. In horizontal motion, there is no acceleration, no deceleration. Since there is no air resistance, the horizontal velocity stays the same, constant. So right here, if I write down this S equals to ut minus ut plus half at squared, then this S for A to B for this entire journey, it is zero. The particle displacement is zero. This U is the initial vertical velocity. Initial velocity means initial vertical velocity because we are considering the vertical motion. A is G here. G acts only vertically. So we have to consider only the vertical motion. So this is UV T plus half GT square. So T here is again the time of flight as long as the projectile was in the air. And you see that if we subject T, this is twice UV divided by G. Twice UV divided by G. Because as time of flight is considered, so obviously G is negative here. G is negative G. Time of flight is considered and the time started from the point A, and at point A the object moves upward. So since it starts its motion in the upward direction, it is moving against the gravity, so G to be considered as negative G. And then by solving the equation, you get the T expression to be twice UV by G, which is nothing but twice U sine theta by G. So see, you get the same expression right here, what you got right there. So if you can apply the equation correctly with the formula, with the law, with the conception, you are going to get down to the same conclusion. Okay. Now, the third equation, I just did it in terms of the, initial velocity, the same can be achieved in terms of the final velocity. Do it yourself, you'll see, you'll get the same thing. Now, the third equation, if we want to see right here, v squared equals to u squared plus twice as. So right now, we are going to consider this v and u for the rising or falling of this object, not the entire path, because this s right here, we want to deal with the vertical height. We want to find the vertical height up to which it can rise. So the maximum height. So this is what we are going to find. And this is why we are considering the vertical velocity finally to be 0 at maximum height. We are not going to consider the entire journey, rather we are segmenting it, either the rising part or the falling part. So right now I'm doing the rising part. At maximum height, the vertical velocity is 0, and uv is u sine theta, which is maximum. It is at point A, and it is rising up, so g is going to be negative g. So now if we just make use of this equation, v square equals to v square, let me make it a little dark, v square equals to u squared plus twice as. Right here we are going to write down as vertical velocity squared equals to initial vertical velocity squared plus 2gh, big H. In terms of s, we write big H here. This is how we symbolize here. So the vertical velocity is 0 at the maximum height, so it is 0. Initial vertical velocity is u sine theta, so it is u sine theta whole square plus 2, since it is rising up, so negative g times h. So if you are subjecting h, you are going to get the expression to be u squared sine squared theta divided by twice g, divided by twice g. So this is the equation of the vertical height. You are not supposed to memorize any of the equations I derived so far. What you need to do, you need to practice it over and over again so that you can get down to this expression. You can finally derive this expression. You are not recommended to memorize this equation. Don't do this. You need to know how this equation is derived. Sometimes the question itself asks how to obtain this expression. Sometimes you will be required to solve some maths, and for that you need to do every single thing step by step to get the full marks. Don't memorize these equations. So these are the things that we did consider in the vertical motion. The horizontal motion we'll be considering in the next video, because this one is getting a little longer. Up to this much, if you have any question, you please do let me know. Ask me, comment here so that I can address this particular question in the upcoming video of the angular projection. And I am leaving it right now. Horizontal motion has not yet been considered of this angular projection. So I'll be considering the horizontal motion now, and then the upcoming video, and then I will be discussing some sorts of questions on angular projection. So make sure that you understand every single thing discussed right here. If you couldn't, please do let me know. Okay. Thank you very much for your time.